Welcome on my presentation about FastAPI hitting the performance jackpot. My name is Maciej Marzęta. I am Python technical leader at Spoton, a unicorn startup. I have almost 10 years of experience in Python, and last 3 years I spent mainly working with FastAPI. After this presentation, you will know what makes FastAPI so fast. So let's begin. FastAPI's performance stands on 3 pillars. Throughout this presentation, we'll discover all of them. And the first pillar is asynchronicity. I believe most of you already know what's the difference between synchronous and asynchronous programming. But to double down that everyone are on the same page, let's do a quick recap. Asynchronous code means that the program can wait for something else to finish, and during that time, the program can pick up something else to do. That's beneficial, especially when making I/O operations, such as sending requests throughout the network, reading, writing files, or making any DB operations. So generally, everything that cannot be sped up by our program. Of course, there's an overhead, because it takes some time to listen to the event loop, which tells the program that some task just has finished and could be picked up. Asynchronous approach is the optimal solution for multiple tasks, which is the case in web applications, because we don't write software to handle one request. We write software to handle thousands or millions of requests concurrently. So, as you can see, asynchronous programming is crucial for performance in web applications. I have good news for you. FastAPI is asynchronous framework. So let's dive into understanding how it is achieved. First of all, FastAPI needs a web server which will serve the application. That web server needs to be asynchronous. WSGI applications are single synchronous callbacks that takes a request and returns a response. This doesn't allow for long-lived connections like you get with long-pole HTTP or WebSockets. Technically speaking, it would work, but it wouldn't be optimal for FastAPI. There comes a need for ASGI, Asynchronous Server Gateway Interface. This allows for features like doing simple tasks in the background without slowing down the main task. It's especially helpful when dealing with tasks that spend a lot of time waiting for I/O operations. So, Asynchronous Server Gateway Interface defines how to communicate between web application and web server, is a successor of WSGI, and is a superset of WSGI, which makes it compatible with it. And in typical architecture, you will see something like that. So clients sends the requests to the web server. Here it is an Nginx. Nginx serves static files, protects from DDoS attacks, load balances incoming traffic, and acts as a reverse proxy to the WSGI server. In this setup, WSGI server, a unicorn, runs multiple ASGI server workers, such as UVcorn with UVloop. Unicorn acts here as a process manager, listening on the port and IP, and transmits the communication to the UVcorn, which converts the data to ASGI standard on which FastAPI relies. So ASGI is required for FastAPI to leverage all benefits of asynchronous programming. So let me show you the UVcorn. UVcorn is an ASGI web server implementation for Python. It supports HTTP 1.1, WebSockets, and relies heavily on UVloop. And there are similar frameworks to UVcorn. For example, we have Daphne, which was originally developed to power Django channels. Or, for example, we have Hypercord, which also supports HTTP 2 and HTTP 3. So let's see what is the UVloop. UVloop is an event loop. UVloop implements Asyncio abstract event loop interface, which means that it provides a drop-in replacement of the Asyncio event loop. It's fast. UVloop speeds up Asyncio a lot. It's even faster than other popular async frameworks like Node.js or Gvent. It's close in speed to programs written in Go. And UV loop is written in Cython and is built on top of libuv, which is a high-performance multi-platform asynchronous I/O library used by Node.js. Okay, so let's see some benchmarks with simple echo server. This chart shows the performance of a simple echo server with different messages size. 3 benchmarks were used: socket, streams, and protocol. And on the left you have asyncio, and on the right you have UV loop. So on average, UV loop makes asyncio from 2 to 4 times faster. And also for 1 kilobyte message, it has 1,000 requests per second. So it's totally insane. It's really fast. And here is the same benchmark, but with results from Golang, Twisted, Curio, Tornado, Gvent, and Node.js. And again, as you can see, it is twice as fast, for example, as Node.js, and is slower only by a little with the Golang. So you can clearly see that UV loop is blazing fast, and it's used in UVcorn, making it performant, making UVcorn really performant ASCII web server. But with the UVcorn, there's one issue. UVcorn code doesn't look cool. You wouldn't like to write your applications like that. Here I show you a simple hello world example. First of all, you need first send to send headers and status code, and also the headers needs to be binary encoded. And then in the second send, you need to send the actual body with the hello world message. That's definitely not handy, and I cannot imagine writing similar code to that on the production. So there must be a better way. But before that, a quote. If I have seen favor, it is by standing on the shoulders of giants. Isaac Newton. So who is the giant on which FastAPI stands? It is Starlet. Starlet derives from, FastAPI derives from Starlet a lot of features that you might not even realize. Starlet is a lightweight ASCII framework, which is ideal for building async web services in Python. It is low complexity HTTP web framework and it has WebSocket support, in-process background tasks, startup and shutdown events, CORS, gzip, static file, streaming responses, session and cookie support, and it has 100% of test coverage, and 100% of the code base is type annotated. So generally, it adds an abstraction layer over UVcorn, so developers can write code with ease. So here is, again, example with UVcorn and with Starlet. With Starlet, there is no need for messy code that you saw in UVcorn example. Just take a look. We define a root, we define a view, which handles the requests, and returns hello world as a dictionary, which is wrapped in JSON response. There is no need to handle all of this stuff, which is on the left. Although, of course, you can set up status codes or encode the body, the response body if needed. So also, the code on the right looks very clear, and some of you might be actually familiar with this, because it looks like FastAPI. Or actually, different way around, FastAPI looks like a Starlet. Of course, FastAPI has this fancy decorators with root, and you don't need to care about JSON responses. You just return the dictionary with this hello world. So generally, FastAPI looks like just a more concise Starlet. And what if I tell you that FastAPI directly uses all features from Starlet, such as background tasks, test client, WebSockets, middlewares, and path converters? What's more, in FastAPI documentation, you can find this statement. FastAPI is just Starlet on steroids. Interesting, right? So let's see if Starlet is fast. You have benchmarks here, total requests per second in Python frameworks. So comparing Starlet to FastAPI and other widely used Python frameworks such as Tornado, Flask, and Django, you can clearly see that Starlet is about 20% faster than FastAPI, twice as fast as Tornado, which was always considered as a really fast framework, and almost 10 times faster than Flask or Django. The links to this benchmark will be provided on the last slide, so we will be able to download the slide and see, because, well, benchmarks are always quite complicated thing to do. And here are another benchmarks with different technologies. So here I added JavaScript Express, Ruby on Rails, and PHP Laravel. And again, Starlet is the fastest one, and FastAPI is close to Express. But of course, Starlet isn't the fastest framework on the earth. Here, I added Rocket as an example, which is 3 times faster than Starlet. And can you guess what programming language it uses? Rust. Bingo. Yeah, it uses Rust. And here are just more benchmarks. I'm checking 99th percentile latency in milliseconds, so lower the better. And again, Flask and Django are performing in the worst way, and Starlet is the fastest one. Here I added again Express, Rails, and Laravel. And again, unfortunately, Ruby on Rails doesn't perform well here. And here again, I added Rocket. As you can see, or as you cannot see, it's so flat that it's almost invisible. So let's go to the conclusions of asynchronicity. Async is an optimal approach in web development, as there's need to handle concurrent requests. UV loop is blazing fast event loop and drop-in replacement for asyncio. UVcorn is a Python ASCII web server which enables asynchronicity and long-living connections. Starlet is an ASCII framework which is highly performant. And FastAPI derives from Starlet and leverages UVcorn as ASCII. So as you can see, every block that is used in FastAPI is really fast, and also FastAPI leverages benefits of asynchronous programming. Therefore, FastAPI is indeed performant. But this is just the first pillar. And the second pillar is data validation. Clients make requests to obtain information. That's the main idea behind the internet and computer science in general. This is the reason why IT plays so important role in current world. Therefore, there is a strong need for handling data, which is one of the key roles of web frameworks. FastAPI addresses this need effectively by using Pydantic. Pydantic is most widely used data validation library for Python. It has over 18,000 stars on GitHub, and as I saw, they are also here as a sponsors. So what's more, Pydantic uses Python type hints for validation. So if you write modern Python, you are already familiar with type hints, and they also integrate well with static typing tools like MyPy and IDs like PyCharm or VS Code. JSON schema can be generated for any Pydantic schema, allowing self-documenting APIs and integrations with tools which supports JSON schema, for example, OpenAPI. It has serialization, so models can be converted, dumped, serialized, and exported in the number of ways. Also, it uses Rust, and in Pydantic v2, all validation logic has been rewritten in Rust and moved to a separate package, Pydantic core. This made Pydantic v2 around 5 times faster than Pydantic v1. And their motto is define how data should be in pure canonical Python, validated with Pydantic. I mentioned Rust, so let's see why Pydantic uses that. Rust is a very performant language thanks to zero-cost abstraction, which means high-level programming concepts like for example, iterators doesn't add any extra runtime cost because they got compiled down to a machine code. There is no garbage collector, but is memory safe thanks to ownership system. it has efficient compilation by leveraging low-level virtual machine backend. Rust can optimize similarly to what's achieved with C and C++, making it suitable for performance-critical applications. And it's low level and gives you precise control over resources like directly managing memory, which opens doors to another level of optimizations that aren't available in Python. So generally, you can think of a Pydantic as the user interface for Rust in context of data validation. And of course, do you remember the Rocket framework from the benchmarks? It was written in Rust. Okay, so Pydantic is used in FastAPI in a lot of places. So let's see all of them. First of all, it's used in path parameters. It's used in query parameters. It validates request body and headers. It does response realization. It's used in dependency injection mechanism and could be used as application configuration with Pydantic settings library. And is used to generate OpenAPI schema. So being more general, Pydantic is used in FastAPI for all the data handling and documentation. So let's see Pydantic in action. Here is simple FastAPI code. Here I define user, which derives from the base model, which is a Pydantic class. Then I have user in, which derives from the user, and we have user out. And 3 endpoints. First endpoints to create user, which is post/users. And here user is annotated with user in. And at that moment, Pydantic does the validation of incoming requests. And if it's valid, then passes to the function body. If not, it will return 400 bad request. Then the user is serialized to dict and used to create user out model, which is also annotated in the function. So as we can see, Pydantic is used here in almost every place. And secondly, we have another function, user ID, is a path parameter, which needs to be an integer and to be greater than 1. And of course, Pydantic is also used here. And in the last endpoint, I have get users, which also relies on the query parameters, which is injected using FastAPI injection mechanism. And also these query parameters will be validated by Pydantic. And what's more, all of these schemas in the /docs will be generated based only on what I defined on the right. Also, we have user's endpoint, and request body and response is well defined as an open API schema. And all of this based on these 3 lines of code. And similar things are happening here. We have validation for the path parameter and then for the query parameters. Okay, so as you can see, data validation in FastAPI is handled well. And these are main factors. First of all, Pydantic, which is data validation library used by FastAPI. Then Rust, which is fast as it compiles to binary code with LLVM optimizations and has control over system resources. And FastAPI uses Pydantic in every place that any kind of validation is needed. So definitely, second pillar of FastAPI performance is indeed performant. The third pillar is flexibility. FastAPI made choices about validation and Starlet, but in different matter, you are free to choose whatever you like. For example, you can choose any ORM framework that will suit you, or perhaps write raw SQL queries if you'd like. You can start small, as your project grows, you can include new solutions that will meet your performance goals. In different frameworks, for example Django, at some point you might realize that Django ORM might not be sufficient for your needs. And then what? In FastAPI, you can easily plug in what you want, as it doesn't force you to write your code in any particular way. A good example is how to define config in FastAPI. You can do it in any possible way, and you are totally free with your implementation. Therefore, I created this monster. In this example, I'm using os.getEnv to get the environment variables, and all of these are held in a dictionary. Of course, I would request changes to that code in any PR, but for small proof of concept projects or hackathons, well, that will just work. Of course, there is a better way with usage of Pydantic, precisely speaking, Pydantic settings. It not only leverages all the perks of Pydantic, but it also fetches the data from the environment or .env files or whatever. Actually, not whatever, but from a lot of places which are a typical place to hold the environment variables. Now take a look at example problem with DB connection. Let's say our application creates and closes multiple connections to DB, which drastically affects application and DB performance. In Django, for example, you would need to look around how it's implemented in Django RM. And if not present there, then you would need to find some hacks to do a custom solution. And how does it look like in FastAPI? Well, you just pick suitable solution from Python scope, and voila, you are done. You aren't bound to framework's decision in any way. And when it comes to RM, FastAPI gives you full flexibility, as it will work with everything that supports Python. So choice is yours, and you can pick up depending on what you already know or what might be the best for you for your use case, as some of these frameworks are faster for simple queries and some are better for batches, etc. So this could be Pony, this could be Tortoise, SQL Alchemy, or Pewee. Choice is yours. Okay, conclusions. FastAPI performance relies on 3 pillars, and as you've already seen, they are really performant. So FastAPI is asynchronous, thanks to UVcorn with UVloop and Starlet. It has blazing fast data handling thanks to Pydantic, and is flexible, so you can choose tools that will perform the best in your case. Therefore, FastAPI indeed hits the performance jackpot. Okay. Okay, thank you very much. You can scan this code to get the slides, also with the references about the benchmarks, and you can also fill a really short survey about this talk. Thank you very much.
All right, you can remember to ask questions via Slido. The room is lasagna, if you haven't found it yet. There's a couple of questions. Let's just begin with the first one. It's about the benchmarking. And in particular, how many requests are you handling with a single UVcorn instance? Is the async claim of thousands of requests really needed? Or whatever is doing 10 to 100 requests per second?
This is a very good question, and it heavily relies on the way how will you develop the application. Because, for example, with the Kubernetes, you can also scale it on the pod level, and each pod will trigger one Junicorn with, for example, 8 UVcorn workers. So that really depends. I cannot provide you exact numbers, because that will hardly depend on the machine resources itself. But well, I think that answers your question.
Do you have any performance concurrency issues with FastAPI? The question says that they had an issue that model validation and converting to JSON happens in the main thread and blocks other requests.
Okay, so again, also I think that heavily depends on the type of the data that you need to parse. Where I work, we mainly have large requests, so we parse them once and then the whole logic flow is applied. But for example, if you would have multiple, for example, time series with thousands of requests, and this JSON parsing will be actually a crucial role, then, well, I can imagine that there would be some errors that you mentioned. However, I haven't encountered something like that.
All right. The next question is, from the scheme, it seems that you suggest to use Nginx plus Junicorn plus Uvicorn, so this stack setup. And won't that increase latency and response time compared to something like Granian?
Comparing to something like what?
Granian.
Okay, I haven't heard that. But well, this is actually a really typical setup, and it's used almost everywhere. You can see it's in AWS examples, and also I consulted it with our DevOps. So hard to say. Maybe that would improve some latency issues.
Yes. The next question is there any way to directly connect the web server like Nginx to an ASGI server, like compared to how you can connect Nginx to a WSGI server?
Well, I don't know, to be honest.
Okay, and then there's what's wrong with dicts as config?
Well, they are mutable. So I wouldn't like an application where in one place, out of a sudden, some configuration would be changed, and that would affect the rest of the code. So, well, I am a strong supporter and evangelist of Pydantic or anything that is more suitable for that.
Are there performance tips for doing performant FastAPI middlewares, like for specific logging?
Okay. Well, so actually, when it comes to the middlewares in FastAPI, you are basically asking about middlewares in Starlet. So the less code, the better. But of course, for example, if you need to add some tracing or logging, then anyway, it's gonna be a little bit exhausting. So, any tips? Try to have the middlewares as thin as possible without adding any additional business logic there.
All right, I love the rapid fire of questions that keep coming in, so let's keep going. Do the difference in performance between Starlet and FastAPI, are they mainly due to the fact that FastAPI does validations by Pydantic and validation in Starlet is slower, or?
Okay, Starlet by default doesn't have validation. So as I previously said, the FastAPI adds additional layers and features to the Starlet. Therefore, Starlet is always going to be faster as it has less features than FastAPI. And only because we add additional validation, even if it's fast, then anyway it's going to add some overhead.
All right, and the last question we have right now is, can we mount the Flask app endpoints to the FastAPI endpoints on an existing code base? And will this cause a performance penalty?
Okay. But why?
All right, that's it for the questions. Thanks everyone for all the questions. Thanks for the talk.